Well, welcome everybody to Wednesday Night Lab. I'm Tom Zinn. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to welcome back to Wednesday Night Lab my friend Paolo Desiati. He's going to be talking with us tonight about celebrating cosmic rays on the 10th International Cosmic Day. Now I get to ask Paolo the 5 questions. Paolo, where were you born?
I was born in Florence, Italy.
So this is when the wave of envy washes over you. And where'd you go to high school?
In Florence.
And where'd you go for undergrad and what did you study?
In Florence, I studied physics in my undergraduate.
And then where'd you go for your advanced degrees?
PhD, I did my PhD in Rome at the University of Sapienza.
And how did you do with the language career?
In Rome? It was a little tough at the beginning, but I got it right.
Way to go. And did you postdoc anywhere or anything?
Yes, I did 2 years postdoc in Germany, and then another 1.5 years here, and then I became part of the team.
So you've been here since 2000?
2001.
Wow.
September 2001.
20 years.
20 years.
It's been great to have you here.
Thank you.
Thank you for coming back. You were here 6 years ago, and I appreciate you coming back. I'd like to thank Maddie O'Keefe, my colleague.
Thank you.
Wisconsin Ice Cube, for nominating Paolo. She said, I have a speaker. I go, oh, who is it? It's Paolo Desiati. Great. So this is wonderful to have you back. And look forward to seeing what you got to say about cosmic rays. Would you please join me in welcoming Paolo Desiati back to Wednesday Night Lab.
Thank you, Tom. Thank you, everybody, for this opportunity. So today, November 10th, is the International Cosmic Day. Usually this is an event that happens in the universities and high schools. It's where scientists and teachers and students usually come together during the day. It's an international event. It happens in Europe, North America, and many other places, to tell students what cosmic rays are, what scientists do, and then to also involve students in some simple research on cosmic rays. 1911, this is the 110 years ago. This is the day where officially cosmic rays were discovered. So in 2011, when we celebrated 100 years of the discovery of cosmic rays, then since then, the year after that, we started with this Cosmic Day event. In fact, 1911 is the beginning of the history of cosmic rays, but it's the end of a long journey. As every time in science, every discovery, even if it's completely random and accidental, happens because something else has brought scientists to do that research. So let me go back a little bit in time and explain you what the context was that made cosmic rays serendipitously to be discovered. As you know, this is pretty straightforward. We can see things because light illuminates them. So our eyes can see light. And so this is, for example, how Galileo in 1609 took a spyglass and pointed to the sky. It was politically very tricky to do that those days. But for example, one of the things he did, he pointed to the moon, and you could see that the moon has mountains, valleys, and craters exactly like the Earth. It was not this perfect sphere that the common philosophy of the time was saying. That's only one of the things he did. Since then, observation astronomy became the one thing. But the point here is that this is optical astronomy. With visible light, just a lens, and very simple instrumentation. So you know that light has different colors. You must have seen rainbow occasionally. And so white light can be separated in all its colors through a prism or through droplets of water during a rainy day. But some colors are invisible. for example, William Herschel, who was extremely curious, he really wanted to measure the temperature of colors. Oh, actually, what he wanted to measure the temperature of surfaces that were illuminated by different colors, light. He found out that red color is a little bit warmer than blue color. But what he actually found is that beyond red, where you cannot see anything, it was even warmer. So something was happening beyond the color that we can see. And by the way, 20 years before, he discovered Uranus. So he really was a very accomplished scientist already at that time, in 1800. In fact, visible light is only 0.0035% of the very vast electromagnetic spectrum, which goes from radio waves, and the electromagnetic spectrum radiation can be expressed, it's described with a wave, from radio waves, which is low frequency, long wavelength electromagnetic radiation, to gamma ray, which is high frequency, short wavelength. And visible light is only one tiny little portion of this vast electromagnetic spectrum. It was 1865 that James Maxwell actually mathematically formalized the theory of electromagnetism, where he unified electricity and magnetism into one theory, which was one of the most powerful and first unification in the history of science, of physics for sure. So you know how your hand looks like if you look at it right now. If you have an instrument that can detect infrared light, you can actually see which part of your hand is warmer than other parts. This is what we use to measure temperature, for example, with infrared cameras. If you go to the hospital, they have a device that detects X-rays, and with X-rays, X-rays can penetrate through soft tissues, and you can see what is inside. You can see bones, you can see if your bone is broken or so. But you can also do the same thing if you look at the sky. We do it the Galileo of the modern time, 200 years later. We point all this instrumentation to the sky, for example, the Crab Nebula, that invisible light looks like just a normal nebula, beautiful, spectacular, but not really exciting if you compare to what it looks like in the different electromagnetic waves, radio, X-rays, gamma rays, and so forth. In particular, X-rays and gamma rays tell the story that inside the Crab Nebula, there are very energetic events, very energetic processes that happen. And I will talk about some of them. And the gamma ray can actually tell, maybe not specifically in this case, but in general, that cosmic rays might be generated in there. Well, maybe the lighting is not great, but if you look at the sky and if you see the Milky Way, it looks so spectacular that it would already inspire you. Imagine if you could have X-ray vision, the sky would look completely different and much more spectacular. Maybe this is what Vincent van Gogh was looking at when he painted Starry Night, who knows? But that's one of the most beautiful paintings, I think, ever done. If you look at the sky in gamma rays, it looks very different again from the visible, from the optical, and from the X-rays. The galactic plane is very intensely illuminated, but you can also see, do you have a pointer? You can also see little dots of gamma rays emission. So there are many, many little point sources of gamma rays, and there's diffuse emission in the plane. Some of these dots might actually be the sources of the cosmic rays, as I will mention later. So here is one of the connections. In the meantime, where people were trying to figure out how wide the electromagnetic spectrum was over the course of the 1800s, radioactivity was discovered. So radioactivity has to do with atoms. You probably know that atoms is formed by a nucleus, very small, which is composed of positively charged protons and neutrons. And then around this nucleus, there's a cloud of negatively charged electrons. It's true that in the ancient Greek language, atoms means indivisible. And it has been believed until the 1800s that the atom could not be formed by other entities, but it turns out that the atoms is actually composed of smaller bricks. So we know we have a periodic table of the elements. where the atom has different number of electrons, different number of protons, different number of neutrons. If you have a combination of protons and neutrons, which is kind of a perfect match, the atom is considered stable. It doesn't change, it doesn't transform itself in time. But sometimes you have too many neutrons or too few. So that gives an instability to this nucleus, the atom, which makes it spontaneously change, transform into something else. That is called radioactivity. Because during the transformation from one atom to the other, something else comes out, some energy. It can be a photon, like gamma rays, electromagnetic radiation. It can be an electron, or it can be a fragment of the nucleus. In this case, a fragment of helium nucleus. This energy that comes out it produces some effect. For example, it's invisible to our eyes as most of the electromagnetic spectrum, but what it does, it produces currents, electric currents in the air that we can actually measure. This is how radioactivity was discovered, for example. There was a transformation of uranium into something else, for example, thorium, and then eventually plutonium, and then eventually radon. And in this transformation, this energy was producing currents or some effects around the experiment. The simplest effect is this ionization, where any form of energy, it can be an electromagnetic wave or a particle, hits an atom and kicks an electron off the orbit. So basically you start from a neutral atoms, and then you end up with a negatively charged electron and positively charged ion, as it is called. If these two charges are in an electric field, they produce a current. If you have an instrument that produces an electric field and measures this current, you can actually measure how much radioactivity is in the air. Sorry, this mask is a little. So that's how radioactivity was discovered. The trickiness was to figure out what kind of energy was flowing through the air that would produce this current. Is it electromagnetic? Is it an electron? Is it an alpha particle? So it was a very complex process, but eventually everything became clear over time. So we do live in a world with very low doses of radioactivity. That's natural radioactivity. We have evolved in there. And in fact, natural radioactivity produces heat within Earth that makes life possible. We exist here not only because the sun produces heat from the outside, but also because radioactivity produces heat from the inside. So radioactivity comes from the ground. And of course, there are those scientists who want to measure what happens if I go off the ground. Do I measure less radioactivity? And that's how the new journey starts. I just give you three people, notions about three people who did this study. One was the German Theodor Wolff, who built his own electrometer to measure ionization currents. And he measured ionization current at the foot of the Eiffel Tower, which was the tallest building those days, and on the top. At that time, it was known how much radioactivity from the ground would be absorbed if you go high. So there was an expectation. He was measuring 17.5 ions per cubic centimeter per second. He was expecting 6, but he measured 15.7. It was less, but not that so much. So that was a little bit confusing for him. Why didn't it decrease? And then Domenico Pacini, he made a measurement of ionization currents on the ground, on the sea, and under the sea. And he found out the radiation strength decreases underwater. But wait a minute, if I go underwater, I get closer to the ground. Should I measure more radioactivity? Why is it less? So he started to have the notion that some of this radioactivity was coming maybe from the air, not from the ground. But the breakthrough happens with Hess, who put one of the electrometers in a balloon, and he made a series of measurements up to 5,000 meters, 3 miles. And he noticed that the radiation actually does increase pretty fast if you go up. So these are the two measurements he did, and he published in 1912 into different locations. You see the beginning radioactivity decreases because you get off the ground, but at some point, some other source of radioactivity coming from somewhere up is increasing. Eventually, a few years later, Cole Herster made measurements much higher in the atmosphere, although he probably risked his life more than Hess got the Nobel Prize for the discovery. 1911, this is the birth of cosmic ray science, although they didn't call it that way yet. It took 20 years to figure out what these cosmic rays are. What is the nature? Millikan thought it was high energy photons, gamma rays. We have already seen them. There must be gamma rays. And in fact, there are gamma rays coming from the sky. I've shown you what they look like. So he wasn't completely wrong. His intuition was kind of right. But then there was Compton who said, no, most of them are not photons. Photons do not have an electric charge. These are electric charged particles. So then Bruno Rossi said, okay, let's solve this. If they're electrically charged, once these cosmic rays get close to the Earth, because the Earth is a magnetic field, this particle with electric charge on a magnetic field get bent. If they bend toward east, they are positive. If they're bent toward west, they are negative. And in fact, they are bending toward east. That's what he measured, and everybody later after him. So these are excess of cosmic rays from west. So they are positive. They are not gamma rays. Most of them are positively charged particles. Not only that, when he made this measurement, he had these counters that count every time a muon cross, a cosmic ray particle crosses, because it produces ionization current. You measure the current, so you detect the passage of something. You notice that you put several counters at a given distance. Many times these counters count particles at the same time. So he was thinking, we are not talking about individual particles. There are many particles happening at the same time. And in fact, a few years later, Pierre Roger and not only they confirmed that cosmic rays are like positively charged particles, but Pierre Roger also found out that these cosmic ray showers can be so vast, they can be hundreds of meters apart sometimes. So we are not really detecting directly the cosmic ray, but we are detecting the byproduct of the cosmic rays, that these particles that enter in the atmosphere. Still a little confusing, but what are cosmic rays then? Well, apart to be, everybody knows that in 1964, this is how the Fantastic Four acquired their superpower. It was because of the cosmic rays. Apart from that, cosmic rays are really all the particles, basically, of the periodic table of the elements, from hydrogen to uranium. In fact, cosmic rays are mostly dominated from the element up to iron, but there are also traces of all the rest. Most of the cosmic rays are thought to be produced by stellar explosion during the end of their life, or very energetic events, massive collision that produce energy that kick these elements out into space at very high energy. So what happens then? These atomic nuclei, which are very well known, and we find them exactly the same in space, right? They're very, very well known here, and they exist everywhere in the universe. They enter the atmosphere, they interact with oxygen and nitrogen molecules, and they produce these massive, they disintegrate, and they produce these massive showers of secondary particles. So cosmic rays do not exist anymore, but what happens later through the atmosphere is this cascade of particles. There are many ways to measure cosmic rays. Typically, let's say you can measure them at the surface with a variety of different instrumentation. You can have an instrument that detects a passage of cosmic ray particle. You can count them. You can detect the time when they interacted and the number of particles and the position where they pass through the instrumentation. Some component of the cosmic rays are penetrating and enter through the Earth. I will talk about this later. So you want, if you put on detectors underground, you can detect this only one of the two residue of a cosmic ray shower. This muon is one of them that can actually enter into the ground. And the deeper you are, the more high energy muon you will detect, because in the meantime, it has lost energy while passing through. But you can also have an instrumentation that instead of detecting cosmic rays on the plane of the surface, you can look up and actually measure the entire profile of the shower. All this huge amount of particles, very fast particles, energetic, propagating through the atmosphere, produce some electromagnetic radiation through, for example, ultraviolet light with via an effect called Cherenkov effect, or radio wave through what is called Ascarian effect. Or the gamma rays produced in this massive shower can actually be absorbed by the nitrogen molecule in the atmosphere that get excited and eventually goes back to this normal status by emitting a lower energy photon. That's called fluorescence. So you can actually detect the fluorescence cycle of the passage of a shower. So in that case, you measure the entire shape of the shower, which gives you much more information what the total energy of the particle is, what kind of particle is, proton, ion, etc., etc. Or gamma ray. So cosmic rays, in fact, I'm implying that it was the first laboratory to study the world of the infinitively small, the world of subatomic particles, as we say now, the world of particle physics. Before the technology was good enough to build these massive accelerators on Earth, cosmic rays were the only source of these particles. Subatomic means everything that is much, much smaller than an atom. Just to give an idea, the size of an atom is about 30 to 300 trillionth of a meter. So 1 meter is 3 feet, one yard. A nucleus is 10,000, tens of thousand times smaller than that. Subatomic particles live in a tiny space, which is a fraction of the size of a nucleus. Just to give you an idea, a human hair is 10 million times thicker than an atom. So you can see the huge disparity of sizes we are talking about. Cosmic rays coming from space, from this large volume of space, can actually tell us something about this tiny little distances world. So when a cosmic ray, primary cosmic ray particle and nucleus hit the atmosphere, it produces a bunch of other known atomic nuclei. If you pinpoint in the periodic table, oh, I know what this is. They are typically unstable and they decay, and they are radioactive, as we said before. But these processes also produce some new particles that they have never seen before. They were completely new. So this is how this hunt on new particles started, something totally new. And it's not really in the cosmic rays. The cosmic rays are relatively simple. It's what they produce that was really stunning for many scientists. New things, they live only for a very short time and then they disappear. And then once the zoo of newly discovered particles was discovered, it was puzzling how all these particles were kind of strangely connected to each other. There were strange properties and symmetry. And scientists put them in these graphs. That means that these particles are somehow connected to each other in processes and decay and transformation that made someone think why they are so connected. They look very different from each other, and yet they are all connected. A little bit like different houses are made from just a few kind of bricks. German and Zweig hypothesized in 1964 that all these different particles should be made from a small number of smaller particles. So they invented and created the concept of quark. Nobody knew if that was true, but somehow the theory was so perfectly matching and it completely explained what people have seen for decades. So the electron, turns out, is still considered an elementary particle. It's not composed of anything else. But the proton and neutrons I was talking about, they are not elementary. They are composed by 3 quarks. And particles with 3 quarks are called baryon. And the proton is the only of those baryons that is actually stable. Everything else, even the neutrons, they decay and eventually they decay into protons. But there are also particles, these new discovered particles, many of them are composed of two quarks, and they are called mesons, and they are always unstable. They do not exist for more than a fraction of a microsecond. So all this was codified between the 60s and the 70s in this elegant model, which is called the standard model. It was supposed to be a temporary name, and here it is again still, where there are the six quarks hypothesized, and eventually one after the other, after the detected experimentally. We have the electron. We already made the electron many, at the beginning of the 1900s. We have the muon, which I just mentioned earlier, and we'll talk about it later. It's exactly like the electron, but it's 200 times heavier. And we have the neutrino, which is what ice cube try to detect. Neutrino coming from the atmosphere, coming from the sky. So basically, and then we have four particles called bosons that are considered force carriers. The photon is the one I was already talking about. The photon is the carrier of the electromagnetic force. When two electrically charged particles or two magnets, magnetic field interact, they actually exchange this photon. The gluon is the particle that is responsible of gluing proton and neutrons together in the nucleus. And the Z and W particles are responsible of all the radioactive decays I was mentioning before. And then we have the Higgs boson, which was discovered finally in 2012. And in 2013, Higgs got a Nobel Prize for it. The Higgs boson is not anymore that mysterious particle, because we know it exists, that actually give mass to each of these particles, except neutrinos, which are a little bit mysterious yet. So the standard model is one of the best predictive models ever made, has an incredible accuracy. It was incomplete when formulated, and all the predictions turned out to be basically true, except in the fine tuning of the model. There are some breaks of the model that are still in understudy. Maybe this is just a representation of a bigger model of the universe, but this is what we have now that describes the microscopic world. Well, let's go back to the large size. But where do they come from? We know they come from space, but exactly from where? So this is a little movie. It is just 1 minute excerpt from a movie from 1957. It was an educational outreach movie directed by Frank Capra. And it's cartoons, there are scientists who present the problem. And there are three puppets representing Fyodor Dostoevsky, Charles Dickens, and Edgar Allan Poe. They listen to the scientists, they tell them what the evidence is, and they try to conclude. So in this except they don't talk, but you can see them.
These galactic clouds float and swirl through the Milky Way all directions. Sometimes they look black and obscure the stars behind them. These swirling clouds apparently create gigantic magnetic fields. Enrico Fermi, one of the great pioneers of modern science. Fermi suggested that within our Milky Way, gargantuan plasmas and so on, which the players are these huge magnetic fields, and the birds are tiny naked atoms shot into space from erupting stars. The atoms are naked because the star heat is so intense that atoms can't hang on to their satellite electrons. They do it at normal temperature. When such an atom is exploded into space from the star, it will eventually collide with a magnetic field. That's all. More speed as field is moving toward it. Years later, it runs into another gigantic field to set shooting off in another direction. Years and so this being batted back and forth. These atoms, there are things, remember their numbers countless, are picked up to almost the speed of light and sent hurtling through our Milky Way all directions.
So this is the description of what is called the Fermi mechanism, where you have a source like an exploding star or some violent emission of energy that kicks off this material atoms with nuclei without electron because the energy is so vast that the electrons are stripped out. And then there are these waves, violent waves of magnetic field, which is very turbulent. So these particles just collide between them. And since these waves move very fast, each collision gives a little bit of an energy to the cosmic ray particle. Eventually, they can reach extremely high energy. So this phenomena, they last millions of years or tens of millions, are extremely efficient. So the way we accelerate particles on Earth, for example, the Large Hadron Collider at CERN, doesn't use magnetic field directly because that would take too much. It uses electric field. You know, if you have an electric field, you can accelerate electric particles. And since these accelerators are round, you only use magnetic field to change their trajectory and make them rotate through this 30-something kilometers circumference. So anyway, cosmic rays are produced by some sources which have been, maybe we just start to identify them now, but this is a very intense research topic nowadays. It can be a galaxy outside of our galaxy, or it can be sources within our galaxy. And eventually cosmic rays accelerating in source collide exactly as it happens in our atmosphere, and they produce this shower. And the only two particles that can actually survive and that we can see are the photons, gamma rays, and neutrinos. I really didn't talk about that, but neutrinos are also a byproduct of the collision and fragmentation of the original cosmic rays. The advantage of these two particles is that they do not have an electric charge. So they move straight through the magnetic fields of space. So when we detect them, if we detect their direction, we can point back to their source. Many cosmic rays that are accelerating instead of interacting and producing photons and neutrinos, they can actually escape from the source. And they're bent by magnetic field for tens of millions of years. So when we detect them, we cannot point back to the original source. We can only measure their mass, their energy, and have an indirect, infer indirect properties of where they might come from, and so forth. So that's pretty much the big picture of how cosmic rays are connected, how we can search for point source of cosmic rays. For example, I showed you the gamma ray sky map where the galactic plane is very intense. If you dim out the diffuse gamma ray, you only end up with the individual point sources of gamma rays. This is just in our galaxy. But there are also point sources of gamma rays outside of our galaxy. Many of those could be actually generated by cosmic rays interacting in their atmosphere, in their clouds around. And together with gamma rays, ice cube detects the neutrinos eventually coming from the same sources. And the neutrinos is really the smoking gun. If a neutrino and a gamma ray are coming from the same source, cosmic rays are definitely coming from there. This is called multi-messenger astronomy, and it's a very big field of research nowadays. So, cosmic rays connect the extremely small world of particle physics and the very large world of galaxy and extragalactic space. What can we do with cosmic rays? Can we use them for our earthly purposes? Let me talk about the muons again. We can use the muons to use, for example. So the muons are this byproduct from the cosmic ray fragmentation. They're one of the few particles that reach the surface from the shower, interaction shower, and can actually enter, it can actually penetrate through rock for tens of kilometers. X-rays that can penetrate through bodies and small, low density objects that cannot go so far. So muons are like electrons, exactly identical to electrons. The only difference, one of the two differences, is that it's 200 times heavier. And the behavior of muons is very well known because the standard model tells us exactly what happens when the muon crosses matter. So we can use our knowledge to do muography. Muography is a very fast-growing applied research field nowadays. And I'll give you just a few examples how interesting this is getting. We are just using muon coming from the sky, from cosmic ray interaction. We know how they're distributed. We know their energy. We know their direction. We know what happens when they propagate through material. So we can use muon for absorption for muon radiography. If you want to know what is inside a massive block of material, if there is some empty chamber or there is something more dense, since muons, when they propagate through matter, they will lose energy faster in denser portions and slower in less dense. You can actually imagine the intensity of the muon. If there is a shadow of muon, it's because in that direction they have been absorbed, which means there is some high density core inside the region. Or you can use the fact that muons, when they pass through denser portion of denser region of matter, not only they are absorbed faster, but they are scattered away at larger angles. So if you calculate, if you have two detectors, muon detector, you expect them to be basically lines, almost perfectly aligned. If there is more scattering because of very dense region inside a bigger mountain, for example, then the scattering angle will be large and you can detect it. So these are the two techniques used in muography. Muon radiography is used in geology, is used in Japan, is used in Italy, is used in many places on Earth too, in the field of volcanology, for example. You want to see what the condition, inside internal condition of a volcano is. In this case, I believe this is a volcano in Japan. You can find out that by detecting muon crossing the entire mountain and putting your detector at the one side of the mountain, you can see that the magma region has lower density than the rest of the mountain. That gives some information to the geologists of what the situation of the volcano is. You can also use muon radiography in archaeology. Already in the 1970s, Alvarez tried to put a muon detector inside the Great Pyramid of Giza, but unfortunately, technology wasn't really that great those days. You need really very high precision instrumentation. That's what happened just a few years ago. The study was published in 2018, a collaboration between Japanese and French scientists. They put the muon detectors inside in the queen chamber of the Giza, Great Pyramid of Giza, and on the outside, like a few weeks or several weeks of detection. Eventually, muon crossed it, and they wanted to see if there are additional empty chambers that have never been discovered before. What they found was, I don't know if you can see, well, they found where the number 7 is, they found a very large, low density void inside the pyramid, just on top of the very well-known famous gallery number 4. And they found another region which looks like to be a very small tunnel that eventually is interrupted on one of the entrances of the pyramid. So maybe these are new chambers, or perhaps they have been new chambers during the construction. They have been filled in with sand or low density material that we do not know. And perhaps the Egyptian government will decide to excavate and search for this. By the way, there is a beautiful novel documentary on PBS Decoding the Great Pyramid that talks about this, and it's great. Muon tomography, which is a little bit different than muon radiography because not only measures how many muons are absorbed, so you can detect more dense or less dense or cavity inside, but you also want to see if muons are radiated more or less. So this was done in Fukushima after the reactor explosion, more than 10 years ago. 2 muon detectors we put on 2 sides of the reactor, and then after 6 weeks, you can see this is after a simulation in this case. You can predict if the fuel is there, then you can see the fuel, the nuclear fuel is so dense that it will absorb and will scatter more muons. If the reactor, which turned out to be the case, has lost its fuel because it's basically punched through the floor of the tank, you will see a void here. That's the technique that was used to see inside the Fukushima reactor, where of course nobody can even get close to. Mining industry is using tomography more and more. Usually the mining industry, they plot the ground with lots of boreholes, which are very expensive. What you can do, you can put some new detectors, maybe in this case with 2 boreholes, and wait enough time to see whether you can detect a very large volume of heavy or metals that you want to mine. And finally, I believe, neon tomography can be used to detect to inspect cargo for contact. I think one of the applications, which probably is already started to be used, is to see if some of this cargo transport nuclear fuel, which typically is much higher density than the cargo itself. So you can have to detect. There is an experiment where a Fiat 500 was put in between, neon detector plates, and then within 10 minutes or half an hour, the lead block was promptly detected. That's another application. Okay, so I don't know how long I took, but I'm almost. So you remember when I was saying that what we detect, cosmic rays detected on ground, are the byproduct of this atmospheric shower. This is also a possible issue in radiation. So for example, this is the ground. If you get higher and higher, the radiation absorbed by humans with respect to the ground gets 10 times more, 20 times more, etc., until you reach the maximum where the shower development happens. And then in outer space is back a little bit lower. So typically, if you travel with on a plane a few hours every several months, it's really not a concern. But technically, the crew and pilot, in average, they absorb about the same amount of radiation that we will absorb in 1 year on Earth during 1 year in their job. So typically, we absorb double than us, which is again not a big issue, but it's something that is being considered for a possible long-term effect. So usually, here is a chart. The blue one is the US annual average radiation loads, which I call 1 here, from all sources. This is where we live, right? It doesn't do anything to us. That's our baseline. Out of this, less than 10% is from cosmic rays. So it's not negligible, it's 10%. If you go to 6 months to the International Space Station, which is above the atmosphere, but still within the protection of the Earth magnetic field, you see that the average radiation absorbed by an astronaut is about 20 times more. If you go to the moon or to Mars on a 180-day transit or 500 days station on Mars, which is outside of the protection of the Earth magnetic field, you are completely hit by a rain of all the cosmic rays you can get. So the radiation absorption for astronauts there is basically 100 times more. That's considered kind of risky, and it's an issue for space agencies to send people out there. So yeah, this is how fantastic form their powers again. Cosmic rays penetrate through the hull of their spacecraft, and each of them got a different power. But basically, the risk of space travel, apart from microgravity, psychological issues, and social closeness and claustrophobia, is the possible effect of radiation from galactic cosmic rays, as I mentioned, or from a lower energy version of the cosmic rays, which are protons, heliums, again, some of the atomic nuclei that are emitted from the sun. The sun emits this wind of particles. The difference between the solar wind and the galactic cosmic rays is the solar wind has much lower energies, but the intensity can be many, many times, millions of times higher than for the galactic cosmic rays. So here we have issues of energy, there we have issues of intensity. And also, I was mentioning that Earth has this magnetic field that protects us from cosmic rays, but also this magnetic field is structured in a way that some of these cosmic rays or particles from the solar wind get trapped. You can see the so-called banal and the picture up there. So astronauts, when they go to the moon, etc., they have to cross this radiation belt. It just takes a few minutes, so it's really not a big issue. But satellite instrumentation that might, especially on a possible low orbit around the equator, they might get damaged because of this high radiation. This is something the space agencies have to consider. So they're working on mitigations, and mitigations of these two big classes. One is passive shielding. So basically try to find a material you can put around a spacecraft to protect the astronauts inside. That is a very difficult task to do because the best shielding is typically very thick bulk of material or very heavy. So that's unsustainable for space agency. But for example, there are solutions, partial solutions to this, like an Israeli startup that built this astronauts radiation protection vest, or there's a huge industry of radiation hardened electronics that you really want to put on your spacecraft, especially if you want to send them to interplanetary observation where radiation can be extremely high and you don't want your satellite to die after years of trip. And there is also this so-called active shielding, where instead of using passive material that will absorb cosmic rays, get it in, you actually generate magnetic field, like the Earth magnetic field, where particles are back away into space. Where a magnetic field will basically generate it around the spacecraft, an artificial magnetic field that would eventually divert back some of the cosmic ray particles, reducing the radiation dose that the astronauts would absorb. And finally, this is a near future problem that has to do with quantum computing. Quantum computing is this brand new technology still under very high research. And it's based on the fact that if you use a normal computer, as we use now, the computer calculation is based on two states, 1 and 0s. All the calculations are based on a combination of these numbers. So all the calculations are basically done in a serially so that these numbers are manipulated to give you the final solution. The quantum computing uses, for example, you can use the orientation of an atom. You can use something that belongs to the microscopic world, where the behavior is completely different from our world. In the quantum physics, you can have an atom that is oriented up or down, which can simulate 1 or 0, but it can also have these two states existing at the same time. That's what quantum computing does. So instead of using all the calculation that has two possible states, you can use calculation that has a very large range of possible states. And of course, as you can imagine, to handle this very delicate state that can be disturbed by anything happening around temperature, that forces quantum computers to work at very low temperature, like 0 Kelvin, 200 degrees below 0 or something like that, and a very complicated algorithm to handle the superposition of states. And the potential is that they can do calculations so much faster, some of the calculations so much faster than a classic computer, that this is a technology where there is a lot of investment nowadays. The problem, the problem is that once the technology problem is solved, that would resolve the technology itself, the material to be used, the right temperature, we still have cosmic ray muons. That eventually, do I have another slide? No, that eventually would hit the computer and would basically break what we say the coherence, or that would break the quantum status that has to be delicately kept in order for the calculation to happen. So one of the possible applications eventually on which that limit, which will take a few years, is maybe to have a similar kind of active shielding where a magnetic field will basically create a muon shadow, and the computer below the shadow will be much more stable, and the coherence of the quantum state can last for long enough so that we can actually use these computers for practical use. Thank you very much.
Thank you very much, Paolo. Questions?
What would be your idea as to what is the origin of the supposed rays that are being used to target U.S. and other embassies in different parts of the world? Do you think that there's any? Do you think that there's any truth to that, or is it just a lot of hype? Thanks.
So the question is what insight I can have on these rays that have been hitting American diplomats in various embassies in the world. It's called the Havana effect because it started in Cuba.
Mostly.
I personally do not know. I'm just reading what it could be. One of the hypotheses is that this might be one kind of electromagnetic wave, for example, microwave, or a form of microwave that kind of resonates with some tissue in the brain that produces this disturbance. And it's definitely some form of energy that penetrates the body of these people and it's released inside that creates a lot of medical issues. But it's still a mystery, or at least they don't really want us to know exactly what it is. But it's kind of an interesting information to have at some point.
Mm-hmm.
I have a rather simple, perhaps hopefully not kind of dumb question here, but if the cosmic rays are all positive, when you expect after 5 billion years of Earth life, the atmosphere would be mostly positively charged, or how does that equalize after receiving all these positively charged?
Yeah, that's a good question. I think what happens is that there's also among the cosmic rays there are actually also electrons, and it's quite a lot of them. The thing I didn't talk about electrons because they really lose energy so fast that they can, but they do enter in large quantity in our atmosphere. And there are also, the atmosphere has a lot of electric currents flowing around, so that the potential is always kind of maintained to a constant level.
One more question, and you mentioned something about some of the particles. All the particles kind of can come as a cosmic ray. This is a question and answer, perhaps, asking for validation. If these things take millions and billions of years to come here, some of the larger particles, perhaps radioactive particles, probably would decay by the time we come here. I mean, they come here. Are they preserved mainly because they're traveling at the speed of light? Internally, basically, time dilation.
Yeah. The question is cosmic rays that have traveled through space for a very long time. If they're radioactive, they will decay and they will disappear. Yeah. So for each element of the periodic table that is represented very well by the cosmic rays, there is always a stable, almost always. Some of the nuclei are not stable in any species. So at least that version comes in. But it's also true that we do detect some cosmic rays, especially a satellite can detect cosmic rays directly before they produce the shower. So that's the best measurement because you cannot know exactly what they are. They can actually measure isotopes of like boron 10, boron 9, and these particles, like boron, for example, is really not an original cosmic rays from their sources produced by the cosmic rays during their propagation interaction. And the other thing, you're right, these cosmic rays particles they travel almost at the speed of light. So their time that if they live for a short time, this time is dilated because of relativistic effect. That might have some effect, but these cosmic rays come so far away that even those times might be not sufficient. So what we detect is basically stable nuclei that can survive these long trips.
Are the predominant number of cosmic rays iron nuclei?
Yes. So if cosmic rays are really produced by supernova explosion by the end of a star, so the question is, cosmic rays are there iron nuclei in cosmic rays? There are. So if cosmic rays are produced by the explosion of a star that is dying, typically when that happens is because all the nuclear processes that start with the fusing hydrogen on hydrogen to helium, then from helium to lithium, lithium to boron. At some point when you have iron, the process cannot continue anymore. So that's typically iron is the last heavy cosmic ray particle that is detected in high abundance. We also have heavier particles, but they are really much smaller abundance in cosmic rays. So we do have cosmic ray iron nuclei traveling through space.
One of your early pictures you had, the cosmic rays accelerated by colliding between clouds.
That's right. Yes.
Now, if they came from supernovae, would it be necessary to have?
Yes, many of them. That's a very good question. This is part of all this research. So many of them definitely disintegrated, especially during the acceleration process, but some of them survive. So we do have a pretty high energy iron nuclei reaching us. So they have survived as such. Yes. Even if it is a small fraction of what originally could have been produced, they still survive, some of them.
I have a question from Raj on Zoom. For muon radiography, how much energy is required to generate them? And does it produce heat? And how is it dissipated?
So typically, yeah, the muon, yes. So the typical energy of the muons in the atmosphere is very well known. I mean, if I say the unit, it's of the order of 1 GeV, it's considered a pretty high energy. This is enough energy for the muons so that they can cross up to 10, 20 kilometers of really dense rock. They lose energy with ionizing processes, so they lose energy relatively slow. That's why they can go through. And this energy can be dissipated in some form of heat, but definitely it wouldn't change the nature of rock because this heat is distributed over a very long trajectory. It's just a small amount of energy per meter.
Then Raj has another one. You might have already addressed this. Do cosmic rays warp, like the space-time warping that occurs because of gravitational forces?
Well, everything that has mass, eventually, if mass or energy, eventually is affected by gravitation. The question is when you have very light particles like muons or even photons, photons have no mass, but they do have an energy. We know that light is bent by a very massive galaxy, but the bending happens in very long distances and with very massive gravitational forces. Eventually that could happen with muons as well, sure, yes.
I think I read somewhere that there's a theory that the fusion process could go beyond iron, and that supposedly in some black holes, there might be extensive quantities of gold and other precious metals that have been produced by fusion processes of that nature. Do you think there's any truth to that? Thanks.
Yeah. So in a star, which is high energy, but not as much as black holes. So the fusion processes can probably happen beyond iron. It's just not energetically advantageous. You need additional, it's typically at lower masses. Every time you fuse to nuclei, you produce energy. That's why our sun is still burning, right? It's still, hydrogen or helium dominated. Iron, after that, it's not advantageous anymore. You need a really massive amount of energy eventually that to happen. And these very massive, enormous energetic processes like collision of of neutron stars or black holes, they might produce synthesized heavier nuclei. It's totally true. Yes, at least theoretically it's true, and it's probably, now there are many spectroscopic observations, you can see heavy nuclei living around these very energetic objects. Yes. In any way, these nuclei exist and they have been produced somehow. So definitely there is some process that can make them up. Yeah.
If not, thank you very much.
Thank you.